Good evening, everybody. Can you hear me? Yeah. Hey. Great. Thank you for coming on this wet bank holiday Monday to the Didsbury Sidebar. Tonight we're very pleased to have with us our speaker, Dr. Stephen Cunnington, sorry.
Common mistake.
Yes, sorry. From Manchester University, and he's going to talk to us about mapping the universe. Thank you very much, Stephen.
Okay, yeah, so thanks everyone. So I guess I should quickly clear up one thing. It says I'm here at University of Portsmouth, but when I registered to do this talk, I was part of the University of Manchester. This is a very recent change in the last, it was on the 1st of April, so literally about 2 weeks ago, I've changed. I'm now at the University of Portsmouth. I'm still living here in Manchester, so I haven't done a literally long commute to be here. I live in Didsbury, in fact, so literally 5 minutes walk away. So very convenient to be here, and it's been on my list for a while to come here and talk with you about my research. So yeah, thank you very much for coming. What I'm going to talk about is how we can map the universe. I'm just going to get rid of this. I assume people can hear me. But yes, I'm going to be talking about how we can map the universe using things like these instruments here. So what you're seeing here is a radio telescope. It's based in the Karoo Desert in South Africa. So I'm going to tell you a lot about this and how we can use these to understand more about our universe. That's what my job is as a cosmologist. So I should probably start by saying exactly what a cosmologist is, because we often get some confusion about exactly what we are. We often get this mistake. So I should say in advance, if anyone wants to come here today to hear me talk about makeup, hair care, skin care, I'm going to have to disappoint you very early. And please, I won't be offended if you leave because of this confusion. So what I often say when addressed with this confusion, which happens more than you think, unfortunately, is I say that I'm not interested in makeup, but I am interested in the makeup of the universe. So this is the over-rehearsed response I give to this. So, and that's, in a real way, that's very much what we do as cosmologists. We're interested in answering quite simple questions, but about the universe as a whole. So that's our subject. So we want to know what it's made of, what its makeup is. We want to know how did it begin, how's it going to end, what's it made of, how is it growing, why is it growing. So these sorts of questions, they're quite simple. It turns out we don't really have very good answers to any of these questions when we apply them to the whole universe. And the reason it's hard to do that is because the universe is very, very big. We literally don't have the language to explain how big it is. So I'm going to try and just spend a few moments explaining how big the universe is on this slide. So we'll start with things we know. So in the top left here, we have Didsbury, where we all are. So all of these measurements here in the bottom right, these are approximate diameters. It's hard to measure the edges of some of these things that I'm going through. But Didsbury, roughly on where you draw the edge, it's about 2 miles in diameter. Okay, so this is kind of a distance we can comprehend, about 2 miles. If we start to go beyond this, it starts to get harder and harder to comprehend distances. So I can just about keep in mind a bit bigger than this. I'm very much in tune with 26.2 miles at the minute because I'm doing Manchester Marathon at the weekend. So I'm going to be painfully confronted with what 26 miles feels like on Sunday. But when we start to go beyond this, it's really hard to have any tangible appreciation for how big these distances are. So when we get to the size of our own planet, which is the Earth, this is about 8,000 miles in diameter. So it's already, at least for me, it's beyond my brain's comprehension. I don't really have much of an understanding of what this distance means. So we're already off to a bad start. We're going to try and comprehend the size of the universe. But our Earth, our planet, sits embedded within our stellar system. We call it the solar system. It's one of 8 recognized planets within this system. And we orbit our central star, which we, of course, know as the Sun. So the solar system is quite a lot bigger than most people think, because it goes, again, it depends how you measure it. If you go right out to the outer reaches of it, you get to a cloud of dust, which we know as the Oort cloud. This is really far out, and it's about 2 light years in diameter, this Oort cloud. So I should briefly explain what we mean by a light year, because some people find this term confusion. It's not a distance of time, it's not a unit of time, it's a unit of distance. So what this means, it takes a number of, how long it takes the light to travel. So light would take 2 years to travel across the whole solar system. And I probably don't need to tell you, but light is not slow, it doesn't hang about. It travels at about 300 million meters per second. So you can really start to get a feel for how big this system is. So our solar system, it's not particularly special. We now know there's many others within our local collection of stars, which is our galaxy. This is the Milky Way. This is what we mean by a galaxy. It's just a collection of other stars. We lie about 2/3 of the way out within this galaxy. And the Milky Way itself is about 100,000 light years. So we're getting pretty big now. So our Milky Way, the galaxy, this is it's not alone. It sits within a big neighborhood of other galaxies, which we know as the local group. So these positions here are quite, or the relative positions at least, are quite accurate. So our Milky Way sits around about here, and it's amongst this collection of galaxies. So we're the second biggest galaxy within this local group. The biggest galaxy is the Andromeda galaxy. So this system, this local group, is now about 10 million light years across. It's absolutely huge. And you start to get to a very important point that we use for cosmologists. Because if we want to observe the universe, you go out to the night sky tonight when it's dark and look up, all the points of light you're going to see are going to be entirely coming from the Milky Way, pretty much. Okay, so we're just seeing our own stars within our own galaxy. But if we want to observe the universe, we need to look beyond this. We actually want to study all of this stuff, the universe beyond. So one of the only few points of light you'll be able to see within our in the night sky, that isn't a star, will be the Andromeda galaxy. It's sufficiently big enough, and it's just about close enough that you should be able to see it with a naked eye. But if you think about what you're seeing when you see the Andromeda galaxy, if you were lucky enough to see it tonight, that light started traveling 2.5 million years ago. Because it's 2.5 million light years away. What this means is that light started traveling before humans existed. Before, humans as we know, Homo sapiens didn't exist. It was Homo habilis, I think. It was around 2.5 million years ago. And throughout the entire evolution of humans, the entire progress of our history has all been going on whilst that light's traveled across the local group, into our galaxy, through the solar system, through the Earth, and into your eyes, which we see as photons. So this raises a very important concept as cosmologists, because what we're doing when we look further back, deeper into our universe, we're peering back in time, which is incredibly useful. If we want to know more about the universe and its past, we can literally see it, which is quite cool, because we're the only type of historians who can do this. We're cosmic historians, and we can just look further back and see our subject as it was in the past. Okay, so this is what I'm going to try and get through within the next, I've put some times up here to roughly predict how long it's going to take. I've got to take them down, but this is what I'm going to try and go through within the next 45 minutes or an hour or so. So I'm going to begin with the status of cosmology, why we already have this quite big problem within cosmology, and I'll get on to what we think dark energy and dark matter are, what the evidence for these things are. This is a big problem, so I'll start to say how we can make some progress with it, I'll get on to how we can probe large-scale cosmic structure as a way of making progress with this, and in particular at radio wavelengths, which is my particular area of research. And then I'm going to spend the last part of the talk discussing the Square Kilometre Array Observatory, which maybe some of you have heard of. It's very got a close connection to this region, I guess. Okay, so let's start with our universe and what we think we know about it. So this is what we think our universe is made of. We've got pretty good evidence for this, and that's what I'm going to try and go through and discuss. So this pie chart is saying that only 5% of our universe is in this, what I call here, normal stuff. Okay, so this is essentially everything you've ever interacted with in your life. So the chairs you've sat on, the tables you're at, literally the light you're seeing me with, all of this stuff is what we'd officially call baryonic matter. Okay, it's just all the elements in the periodic table and all the things that particle physicists have some sort of explanation for. So we kind of know what this is, but this only makes up 5% of the universe. The remaining 95% are in these mysterious components, which we know as dark energy and dark matter. I'm going to talk through exactly what we mean by these components. So what is the evidence for this? So we'll start with dark energy for why we think we need this. So in order to explain this, we can go back really to, this is probably what most people would describe as the birth of cosmology, around about this time. So it's nearly about 100 years ago, which is quite young for a science when you think how old most scientists are. So this was Edwin Hubble, who's an American, and he and his colleagues, they just about developed the technology to be able to see distant galaxies beyond our own, and then chart their positions, essentially. And that's what is being done here. This is the original plot from his paper, nearly 100 years ago. I'm just going to fast forward a few decades just to get a bit of a nicer plot. So it's the same thing that he's showing here, but just with more modern data. And what's being plotted is each point here is a galaxy, and it's plotting the distance on the x-axis, and on the y-axis, it's plotting their velocity, which is relative to us. So they're how fast they're moving away from us. And what you'll see is there's this nice line suggesting that the further away galaxies are, the faster they are moving away from us. Okay? When you start to think about this and let this crystallize in your head, it's kind of a strange conclusion. So yeah, I see a hand up.
How far away the planets are?
Fantastic question. So in terms of the distance, we can measure that by essentially their brightness. So if I'm holding a candle, if I hold it very close to you and very far away, you kind of get some sense of how close it is. It's pretty much the same process that we're doing in this test here to measure how far away they are, because we know how bright some of these things are. So when you think about this conclusion and what it means, it's slightly unsettling because it kind of means that we're in a special point in the universe. Everything's moving away from us evenly in all directions. So you might sort of start to think, well, we're at the center of the universe. Maybe we're where the Big Bang happened and everything's moving away since then. But as scientists, we don't really like these conclusions because they're too fine-tuned. They need to be too perfect. How do we get so lucky to be at the center of a universe? And if you have to be at the center, that kind of means the universe must have an edge, which also doesn't really make sense. So this is not a conclusion that we really like. So it comes to this question. So how can everything be moving away from us without us being at a special point in the universe, without us being right in the center? So to answer this question, we need another great mind, one of the finest minds of our generation, which is, of course, Paul Hollywood. So anyone who watched the Great British Bake Off, you will know that Paul Hollywood, he loves to bake bread. So he really likes to bake bread. In this case, he's baking bread with some raisins in. And the reason Paul Hollywood knows the answer to this question is because when he bakes his bread, which in this analogy, you can imagine the dough of the bread is the universe, what's going to happen is the dough is going to expand. And if you notice these raisins in the middle, in the case of the analogy for the universe, if these are galaxies, you'll notice that, as the dough is expanding, or as the universe is expanding, all of these raisins are getting further away from each other. So if you are living on one of these galaxies or these raisins, you would conclude, as we've just concluded, that all the other galaxies are moving far away from you. And if you notice, the ones further away are moving away from you at a faster rate. Okay, so this is exactly the conclusion that we come to with our own data on galaxies. So what this means is that this is very strong evidence that the only way you can really explain the situation is if the universe itself is expanding. Okay? The very fabric of the universe itself is growing, and all the stuff embedded within it is getting further apart. Okay, so we've sort of known this. This has kind of been the logical conclusion that we've fallen on for well, pretty much since the day of Edwin Hubble. This is one of the first conclusions he made. And this led to more questions. So if the universe is expanding, maybe this was an after effect of the Big Bang. So the Big Bang was the start of the universe, where we had this rapid phase of inflation. So fair enough, maybe that's expanding, and the universe is still expanding from that point. But if you think of what's in the universe, it's all filled with stuff that feels the force of gravity. So you kind of think that all of that mass is going to start to suck the universe back together. So in other words, that expansion should be slowing down. And this is exactly what this team, just at the turn of the millennium, tried to test. They wanted to see if the expansion of the universe is slowing down because of all the attracting matter within it. So the way you can do this test, you can play the same game as we've explained. You know the distance to a lot of galaxies, and you also know their velocity. This is just called redshift, by the way. But you can play the same game. What you can do now, if you go to far enough distances, keep in mind that the further back in distance you're going, the further back in time you're looking. So the expectation was that as you go further back in distance, you're looking further back in time. So galaxies in the past should be moving at a faster rate than they are now for a constantly expanding universe. In other words, these galaxies should start to be in this red region of this plot because they're moving at a faster rate in the past. However, as you can see, the exact opposite was found. So this is saying that as you go back in time, galaxies are actually slower in the past than they should be if the galaxy was just expanding at a constant rate. So when you think about what this means that the universe's expansion is accelerating. This was a very, very strange conclusion. It actually led to the Nobel Prize. It was 13 years later because no one was really sure it was true at the time. So it took 13 years for everyone to conclusively prove it, but it did win the Nobel Prize. And this is the conclusion that we're left with today. That the universe is not just expanding, but that expansion is accelerating. Yes, as I said, this won the Nobel Prize. It was 13 years later. It's these guys here. I think it's 2 Americans and an Australian. So this leads to the next question, which is kind of where we're up to today. This is the question that all cosmologists are trying to answer. What is causing this accelerated expansion of the universe? So this is kind of where we get to. This is the end of the story, really, because we don't know. Is the short answer for this. All we've done so far is we've given it a name. So we've called it dark energy, and I have no idea what to use as a picture for dark energy because we don't know what it is. We don't know if it's a force, a modification of gravity. So I always use this picture, which is a real beer, apparently. I've never got my hands on a bottle, so if anyone can, please let me know. But yeah, I really like the slogan of this bottle. I don't know if you can read it from the screen, but the slogan is, without it, the cosmos would be inexplicable. So in terms of what we actually think as physicists, what dark energy could be, of course, we have a number of theories. It's an absolute, theorists have a field day with this kind of stuff. There's a new theory every couple of weeks of what it could be. And they kind of range from things like it could just be that we're wrong about gravity. It could be some sort of energy coming from the actual vacuum of space. So as space grows, you get more of this energy and you get this runaway effect. And there's all these various kinds of crazy theories, which most of them I don't understand, to be honest. Okay, so we're kind of up to speed with dark energy in the sense that we don't know what it is, but we know it's what we say is behind the accelerated expansion of the universe. And we know it must have this content from doing various tests on molecular structure, which I'll go on to talk about as well. So this leaves dark matter. So dark matter, in a way, is, well, at least for me, I kind of find it a bit more easier to understand why we need dark matter. It's more of a tangible thing. So the evidence for dark matter, it was Vera Rubin, probably the early pioneers of this, I think in the 60s. And she did this by looking at rotation curves of galaxies. These are collections of stars now, we're going back to. And what she looked at is how these galaxies rotate. So what's showing here in this animation, that you can see, each of these points of light is a star within the galaxy. And Vera Rubin was plotting the distance from the center versus their rotational velocity. In other words, how quickly they're moving around in this rotational pattern. And what we think we know about gravity and what we can see from these, how much mass is within these structures, we predicted that these galaxies should have these rotation curves, where the stuff in the middle is rotating much faster than the dust and the stars on the outside. What's really peculiar is that Vera Rubin and her colleagues actually found this much flatter type of rotation curve. So in other words, the stars around the edge were rotating much faster than they should be. This is really confusing at the time because these systems should really be unstable. In other words, the stars on the edge should really be being flung out. They're rotating too fast. So the only way you can really explain this is, one, either gravity is wrong, but we have very good tests of gravity. It's Einstein's theory of general relativity. We think it's very well understood. Or you must have some missing mass within all of these galaxies that's essentially holding all the galaxies together. It's kind of acting as like a cosmic glue within the galaxies. So this is what we think dark matter is, this cosmic glue. Again, similar to dark energy, we have all of these different theories for it. We kind of think it's going to be some sort of particle. So someone at CERN, the Large Hadron Collider, they'll hopefully soon, in the next few years, find a dark matter particle that's very weakly interacting. We know it doesn't interact with light, that's why we don't see it. But we know it must interact with gravity. That's why it holds these galaxies together. So yeah, most of these theories are really kind of just particle physics theories of what this dark matter particle could be. And then similar to dark energy, we also have an alcohol named after it, apparently. So this is a spiced rum. So this is stronger percentage. I don't know what that says about it. I guess you have less dark matter, so you need more of it to have a good time or something. I don't know. So this is the picture of our universe then. So yeah, dark matter. This is the missing mass holding galaxies together. Dark energy is the accelerating expansion of the universe. But we don't know what either of these things are. So this is the problem with cosmology. And it now gets to the point of how do we make progress with this? How can we address these questions? That's probably a good point to see if there's any more questions.
Is dark matter counterbalancing the effects of dark energy, or are they just different things that work in different ways?
Most people would say they're completely different things, and they're unrelated. But there are some fringe theories. That's probably a bit of an unfair statement, but some people think they are interacting. There's interacting dark energy theories where they think these two things interact, but that's not necessarily the mainstream belief.
Yeah, I was just getting based on the age of the university about in billion years. And the latest, but the latest findings in the James Webb telescope that the universe could be older than that, and that would reduce the amount of dark energy and dark matter needed the universe the nodal model.
Exactly. Yes. Yeah. So this is kind of making the assumption that the universe is just under 14 billion years old, and JWST is very interesting because it's making. For people in the audience who don't know, JWST is this fantastic space telescope that's able to see very, very early forming galaxies. And it's kind of seeing galaxies that are forming so early on, the universe must be older to explain them. And I guess the jury's still out for some of these questions, because if they are proved to be too old, then the universe must be older, and that will adjust some of these percentages for sure. Yeah. Yes?
Is it possible to predict where the Big Bang actually happened? Because using your analogy of currents in a red thing, if we're somewhere on that scale of going outwards, surely the outer galaxies are moving away faster from us than the ones more inward.
Yeah, so I see your point. This is a good question to ask, because it really addresses the nature of what the Big Bang is. So I'll just spend a few moments explaining what it is. So the Big Bang, it didn't really happen in the center of some space that already existed. The Big Bang was literally point-like and included all the space that ever existed. So when you think about it, the Big Bang really happened everywhere. Just all of the space around us was just all on top of each other. And it's rapidly expanded and become the size of the universe. So you can get into philosophical conversations about how and that can be an infinite universe and things. But essentially, to address your question, the Big Bang didn't happen, here. It literally happened everywhere, because everything was just on top of each other. So all of space was collapsed to a point-like structure. Okay. So these are great questions so far, so please keep them coming. So yes, how can we make progress with all these problems that you're rightly pointing out and asking questions that go right to the heart of them? So one way is by doing this idea, which is very closely related to my research, and it's probing large-scale cosmic structure. What do I mean by this? So I kind of touched upon it already, I guess, when I showed the slide showing different scales of the universe. When you get to a big enough scale, beyond galaxies, beyond local groups of galaxies, the universe's structure begins to look something like this. You get like a cosmic web distribution of structure. And the reason this is very interesting is because how this evolves and across different scales tells you an awful lot about how gravity works. It tells you literally about the composition of the universe as well. So this is actually how we get those percentages that I showed in the pie chart, this 25% dark matter, 70% dark energy, for example. So this is incredibly useful to try to probe. This is exactly what many cosmologists like me are trying to do. So one way we can do this, one way we can analyze the large-scale cosmic structure is if we can observe it, we can then compare it to our theoretical models, our theories, essentially. So this is very much how we essentially play God. Okay? So we now have the sufficient computing power to essentially build universes within supercomputers. Okay, so the way this works is into our coder's model of the universe, we pour all of our theories of gravity, what we think is within the universe, so dark energy, dark matter. We can tweak all this as well to test different theories. We can try and build a universe without dark matter, for example. And we push this all into a supercomputer, set some initial conditions for the universe, and essentially press play on this thing and let the universe evolve within this computer. And it will solve all of these equations, build this structure, and that simulated universe it spits out at different times. We can then compare that to observations and then see how close we are. And it's these kind of tests that is another very strong piece of evidence for the existence of dark energy and dark matter, because we really struggle to build universes without these components. So I have a quick example of how this works. This is a real simulation. So you'll see in the top left here, this parameter Z is for redshift. So you can just think of this as like the time of the universe. So when Z, this will count down to 0, which means it's getting closer and closer to the present day. So this starts at Z of 20. So this is when the universe was approximately 1/20th of its size that it is today. You see this is on huge scales here, across about 163 million light years. So as we play, this will start to progress. So the supercomputer is solving all of these equations, constantly evolving all of these particles within the system. And you can see this structure start to develop and become ever more complex. You see these big filaments start to appear, big central dense regions, and these big voids appear as well. So this is exactly what we do. We can build these universes within our computers and then compare the output to exactly what our observations are telling us. And this kind of gives us an idea of how close we're getting to a theory of the universe.
Excuse me, I'm
Yes.
sorry.
Just
To check I've understood, which is a very simple thing that I just want to double check I understood. So what you were doing then was going back in time and starting from a model of going back in time and then coming towards now and modelling how you thought the universe would be, and it's changing like that.
Exactly, yeah. So when Z is 20, that's the olden days, if you like.
Yeah.
You know, however many billion years ago that would be. And then we're not really evolving it ourselves. We're just, the computer's doing it for us, right?
Yeah,
We
gotcha.
fed all of our, what we think we know about the universe, and then it's just playing. And when we get this out the other end, so yes.
Very, I'm sure everyone.
Yeah, no, it's always good to ask. There's probably always someone else in the audience who had the same question. Okay, so this is how we can analyze large-scale structure. In order to make this process worthwhile, we need to be able to actually observe it as well, so we can match observation with theory. Okay? Otherwise, this whole process is fairly pointless. So how do we observe large-scale cosmic structure? Because this is quite a subtle point, which is often overlooked when I hear cosmologists talk. Because most of, as I've just explained, most of the universe is structure. Most of its matter is made up of dark matter. We can't see dark matter, okay? So if you want to try and probe the foundations of the universe, this large-scale structure, you're wanting to try and observe dark matter, which we can't do. So if you went and did a survey of this, you just get something that looks like this. You get darkness, right? You can't see dark matter. So you need to do something a bit more indirect. So this is what we do. We go out and we chart the positions of loads of traces of the dark matter. In this case, it's galaxies. This is a cartoon. I know there's stars here, but these stars are representing galaxies, okay? So they just point like galaxies. So if we detect enough of these, and we can detect their positions in 3 dimensions as well, we obviously know their angular position on the sky, and we know how far away they are, so we can get a 3D map of these galaxies. And what we know to be the case is that these galaxies, they will trace the underlying dark matter field. Okay, so you see here, these cartoon galaxies are falling on the peaks of the underlying structure of the universe. So what we can do is we can do some statistical analysis of the distribution of these galaxies. And by doing that, we are indirectly probing the underlying large-scale cosmic structure. Okay, so this is how we do this. So, yes, please.
To me, it seems like using iron filings to film magnetic waves that you can't see.
Yes, that's quite a good analogy, yeah. Another analogy I always like to use is we can't, if you're aliens trying to map the population of people don't emit light, so you can't see people, but they can map streetlights. So streetlights from all over the city, and you'll see very dense streetlight patterns coming from London, from Manchester. And you can map the population by doing it. So it's all exactly like this. You're just trying to find a tracer of the underlying field that you can't directly see. Yeah, it's a good analogy. So this process of detecting all these galaxies to trace the underlying dark matter, large-scale structure, this works really well. We've done this now for a couple of decades. So what this slide here is showing is the same story as before. We have this underlying dark matter field. That's the stuff we want to trace, detect. We can't do it directly, so we have to detect loads of galaxies. What this animation here is showing, it's kind of starting to address the problem. What you need to do is detect many, many thousands, millions, in fact billions of galaxies to do this well. If you don't have enough, you're not going to get a very good sample of that underlying distribution, so you're going to do a poor job. This becomes a very, very expensive process. If you want to do this over very, very large scales, which we do as cosmologists. We want to go to very big areas and go very deep into the universe's history. You need to detect billions of galaxies. So this is a real problem, but I mean, people are trying to do it. There was a nice news story, probably, I think it was on BBC News. I think it's got quite widely reported, but the Dark Energy Spectroscopic Instrument, it's an instrument called DESI. This announced some news saying that dark energy was evolving differently than we think. And this is doing exactly this process. It's detecting loads of galaxies to do exactly this job. But what do we do if we want to improve this? If we want to go to these bigger volumes, go to these greater depths, we need another approach. And this is exactly where my research comes in, which is trying to say, well, what can we do beyond this? So the alternative to this, what I call galaxy cataloging approach, is what we call intensity mapping. So what you're doing here is, rather than pointing your telescope at galaxies, taking a long time to record the position to them, you're instead just scanning the sky quite quickly, and you're just recording all the combined unresolved emission entering your telescope. And you build up these kind of blobby-looking maps like this. They're much more humble-looking maps, but they're still very useful. So, if you look at a particular blob of emission, you no longer know how many galaxies have contributed to that blob. But what you can assume, and we know this to be true, is that there's a lot of structure behind that blob. So you can play the same game. You can do some clustering statistics or whatever you want on this field. And then because it's a tracer of the underlying dark matter, you are indirectly probing the large-scale structure. But now you can, sorry, one sec, you can now do it over such much larger volumes. Yes, sorry.
Wait, could you explain what unresolved emission is?
Yes. So what we mean by unresolved emission, we just mean, so with a galaxy, we actually resolve its position, so we know it's exactly there. With this, we don't resolve it. Yes, it just kind of fills the whole lens of the telescope, and we just got big blobs of emission. That's what we mean by that. Cool. Okay. Yeah, this is a great question because this leads very nicely on to exactly what we do measure. So you can do a number of different techniques. In this example here, you'll notice I've used a radio dish, so that's giving a hint to what we're going on to. But what we essentially do is we're looking for a frequency coming from a particular source that's tracing the underlying. It probably works best if I go on to the next slide because it will explain exactly this question of what it is we're actually looking for. To do this, I need to explain exactly what we mean by radio wavelength cosmology. Or, I mean, you can apply this to any field of astronomy, radio astronomy. Because most telescopes, and most of what we think of when we think of a telescope, we think of looking through an optical lens telescope. So by optical, I just literally mean visible light. All the colours of the rainbow, right? All the colours you can see. But that's not the only colours available. That's not the only source of light coming from space. It's literally coming from all of these different wavelengths. So in other words, different colours. So whenever I say wavelength, you can just literally think of colours. A lot of these colours we can't see. So radio waves, they are just another colour. They're much longer wavelengths, but they do travel through our atmosphere. They're not opaque to this emission. So we can build radio telescopes on the ground to detect this stuff. And it is just another form of light. So I have to debunk this myth here, which a lot of people get confused about. I don't sit there and listen to my radio telescopes. It is just another form of light. Okay. So Hollywood has a lot to blame for this. And I think this is contact. I think I've not seen it, but there are lots of other movies doing this where people are listening to radio telescope, and it really annoys me as a radio astronomer because this isn't what we do. We literally just receive the light into these radio dishes, and then we see their images on the screen that they're making. So why radio? Why is it useful to build radio telescopes? So this speaks exactly to the question the gentleman was asking at the back. What we can look for with radio emission is signature signals of hydrogen gas. So this emits a very distinct wavelength of emission, 21 centimeters at wavelength. And just to give some background science, which isn't too important, but it's showing exactly where the signature comes from. Hydrogen in its neutral form, we will have one electron and one proton. That's why it's neutral, it's electrically neutral. And what this electron can do, it can undergo what we call a spin flip, just a spontaneous event where it drops to a slightly lower energy level than its structure, and then it will emit this 21 centimeter photon to balance the energy equation. So all you need to know is that whenever we see this 21 centimetre emission, this wavelength at this particular sorry, this light at this particular wavelength, we are seeing a signature of neutral hydrogen gas. So this is very useful because, as anyone who's ever seen a periodic table before, you'll know that hydrogen is number one in the periodic table. It's the most abundant element in the universe, at least the baryonic elements of the universe, I should say. So it's everywhere, hydrogen. And very useful for us, it also remains essentially within inside galaxies in the late universe. So whenever we see this 21 centimetre emission, we know it's coming from within galaxies, and we know those galaxies are tracing the underlying structure of the universe. So this is an ideal tracer of that large-scale structure. Yes. So yeah, so it's from this process here. So what it's doing, it's neutral hydrogen can just spontaneously do this transition from its electrons. This is just like it's a quantum mechanics process. So its electron can undergo this spin flip, and essentially when it does this, it's dropping to an ever so slightly lower energy level. So it's essentially then a lower energy system. And in order to do this, it has to free up some energy. So to do that, it releases some light. So it just spontaneously, every now and then, it's a very rare thing. It's actually every 1 in 8 million years, I think it's happened. There's a lot of hydrogen that we see it. So very rarely, it will emit these sparks of light at this very precise frequency, this 1.4 gigahertz or 21 centimetre wavelengths. So it's very much a signature of just future hydrogen. Yes, yeah, I can tell. Yes, someone knows some astronomy. So yeah, you're exactly right. So I think I can explain that on the next slide. But when this light is emitted, when it's traveling great distances across the universe, and that universe is expanding, that's literally going to stretch this light, which is actually very useful for us because it means this is how we measure the distance to it. But so this is it's not a it's not something that's hurting us. It's actually something that's helping this process of redshift. So this animation might help to answer some of these questions as well. But it's the same as before. We have a distribution of some cosmic web with all the galaxies tracing that cosmic web. We want to try and map this. So how do we do this? Well, as I've just explained, within inside most of these galaxies, if not all of them, there will be these large clouds of neutral hydrogen gas. It's very abundant. And this quantum process, where you get this energy spontaneous transmission going on, will emit these 21 centimetre photons. These stream across the universe, and because the universe is expanding, they're redshifted along the way, so they are slightly stretched. And we can then use the radio telescopes, because they're still within radio wavelengths, to detect these photons. And we scan the whole sky, trying to look for this emission as much as we can. We build up these maps of emission. Then because of the fact that they're redshifted, and the amount they're redshifted by depends on how far they've travelled. If they've travelled from very, very far away, they're going to go through more expanded space, they're going to get stretched more. So the more redshifted they are, the further away they are. This is how we build up these three-dimensional slices across these maps. So by combining all these together, we literally get a three-dimensional map of the underlying large-scale structure. At least that's the idea. Okay. So that's how we can probe large-scale structure at radio wavelengths. Just check in, see if there's any more questions before I move on. Okay, so for the rest of the talk, which could be 15 minutes, it's going to be talking about the Square Kilometre Array Observatory, which I'm sure some of you have heard of. So yes, the SKA, it's this huge international project, which is trying to do exactly this. It's trying to do this radio intensity mapping amongst a whole other science cases. Unfortunately, it's not just a telescope that does cosmology, as much as I wish it was. But it is one of the things it's going to do. So the SKA comes in these two components. It has one of its parts of its telescope is based in South Africa in the Karoo Desert, and another part is based in basically the outback in Western Australia. So these are some of the most human remote places on the planet, and it may be obvious to you why we do that, because whenever you have humans, you have mobile phone signals, you have Wi-Fi, all the things as radio astronomers we hate. So we try to put them in very, very sparsely populated regions, so we get very little contamination. So it's this huge project trying to build these two telescopes. It's under construction now. What's very exciting for us as local residents of Manchester is that the global headquarters for it is based at Joggle Banks. That's just 20 miles south of here, roughly. So if you haven't been, it's a great place to go. It's got a visitor centre there, which is really cool. I think this is me at the visitor centre, being very pleased to be in front of the Lovell telescope. And you'll notice these SKA logos all over the place, because the global headquarters is right next door in this very fancy new building, which is, I think they opened it in about 2018. It's very new. So, as I said, the SKA will explain that it comes in these two components, these two different sites. The reason we do that is because it's doing all of these different types of astronomy. You want to have different telescopes that look for different stuff, essentially. So the thing I'm most interested in is the part in South Africa, the SK Mid, which has these more conventional satellite dish type telescopes. And the reason for that is it's probing the frequencies or the wavelengths or the colour that I like in terms of the radio region. So this is right in the sweet spot for doing 21 centimetre intensity. So this is what the telescope is going to look like. It's going to be this array of dishes. It's going to be about 200 dishes in the desert. Some of them vast distances apart. I'll explain why that is in a minute. But the thing I like most on this slide, which really speaks to the challenge of this type of project, is just how much data we're going to get from these telescopes. It's quite staggering. It's scary, in fact. So it's going to give us 8.8 terabits per second. So if you're like me and this doesn't mean too much to you, I've done this conversion down here. This is about equivalent to 4 times the UK internet consumption. I think this is for the last calendar year. So an enormous part of the challenge is just working out how we're going to deal with the data this telescope is giving us. And bear in mind, it's also in the middle of the desert, so it's not like we're, in Silicon Valley, where you have all these this infrastructure to deal with this kind of data rate. We're in the middle of nowhere. So it's an enormous challenge trying to build the infrastructure to deal with this kind of thing. So yeah, as I mentioned, this is under construction now. We have, I think this timeline is a little bit out of date. This is available online, I think. And yeah, we're technically now here. So I won't go into all details on this, but we should have about 8 dishes down by now, I think. And I think there's only about 4 down with 1 operational. So a little bit behind this, we've got some catching up to do. But broadly speaking, this should be built and ready within the next 3 years or so, depending on what you mean by ready, I guess. However, if you're impatient, like me, we don't necessarily have to wait all this time for the SKA to be built. But what's really cool is they built essentially like a mini version of the SKA. And that's already on site, and that's what you're seeing here. So this isn't an animation, this is real time-lapse photography in the Peru desert. And this is the Meerkat telescope. So this is an array of 64 dishes. So slightly smaller than the SKA, it's about 1/3 of the size of the final SKA. But it's on the exact same site as it. And this is done by design, because the idea is that SKA, it's being built around Meerkat, and the final version of SKA is going to incorporate Meerkat. Okay, so the final SKA will be like 130 dishes, plus the 64 from Meerkat, and then you get roughly 200. So this is what we're using now. This has been built for about 5 years now. It's quite a mature telescope. It's giving us great data already. And this is very much what I'm involved in with my science. So yeah, we've adopted this guy as our mascot. I'm guessing most people know who he is. He's from the adverts. What's really weird when I do international talks, people are very confused why I put a meerkat in a waistcoat, because I don't think this advert is available abroad. But an interesting side note as well on the name Meerkat, it may seem obvious, but even before Meerkat, they had the Karoo Array telescope. So this was just a smaller 7-dish array. That was the Karoo Array telescopes, that was cats. Then they developed the plans to have a bigger telescope, so they wanted more cats, and the Afrikaans word for more is meer. So it became meerkats. So it's got this really nice, quite poetic double meaning, at least, well, certainly compared to other telescope names, where we've got the very large telescope and the extremely large telescope and boring names. So I think this is quite cool comparatively. Right, so one thing I haven't really spoke about is why we have an array of dishes. Why don't we just have one big dish? So the reason we do this, at least for most of the science cases, is because with radio telescopes, if you combine lots of them together, you can get very, very good resolution. You can detect very, very small things. This is nicely demonstrated by this here. This is the Event Horizon Telescope project. So what they did here is they took all these pre-existing radio telescopes, literally all across the world. And the idea with interferometers is the bigger you can get these separations, the better your resolution. Okay, so the better you can see small things. So that's why they're literally making these global separations. They're called baselines, the separations between these antennas. You're getting these global baselines all across the world. And by doing that, you can achieve the resolution good enough to see a black hole in another galaxy. So this is a really cool project and demonstrates just the power of having these interferometers. So that's primarily what SKA and Meerkat are going to do, is have these arrays working as interferometers to be able to see galaxies, tiny little things as well at great distances. But for me, as a large-scale structure cosmologist, I'm actually not really that interested in the tiny, small scales. I need the really, really big volumes of sky. And this is where the interferometer actually becomes a bit of a limitation. Because the other thing with interferometers is what we call the field of view. In other words, how much you can see. That is defined by how short your baselines are. In other words, how tightly packed all of your dishes are. And for Meerkat and the SKA, they're not sufficiently tightly packed enough to give us fields of view necessary for doing very, very large-scale cosmology. So this is a bit of a problem. And the way we get around this, we're the only science collaboration who does this with Meerkat and SKA, is we take this very lovely designed interferometer that people have spent years trying to work out the exact spacing of all the dishes. And we say we don't want to use it as an interferometer. We just want to use it as a collection of 64 dishes or 200 dishes in the case of SKA. So we now have like 64 telescopes. And the reason we do this is then literally the sky becomes our limit. We can then just steer these dishes, scan the whole sky, and get as much of the much field of view as we like. We also have the additional advantage that we now have 64 telescopes, right? So if we get one night's observation time with Meerkat, we essentially have 64 nights. So we can very quickly build up our observations. The small sacrifice we have to pay is that our resolution is not very good. So we get these very poor resolution maps with this like very blurry field, I guess. But if we're just interested in the very large scales, that's not too much of a problem for us. So this kind of crystallizes how we use Meerkat. So you essentially get a map of the sky for every single dish. So you'll notice here, if you count the panels, there should be 64 panels. That's one for each dish. And what's happening here, it's sort of showing the scan pattern that we do with Meerkat as well, where we scan across the sky in different directions to build up this emission. So this is now real data I'm showing you. This is from our first pilot survey that we did, where we're trying to demonstrate this new intensity mapping technique, that it can work. You'll notice some of the dishes have much more data missing, and this is mainly due to what we call radio frequency interference. This is RFI. This is contamination coming from mobile phones, planes, satellites, all these sorts of things. We, in most cases, just have to delete it when it's in our data. It's just too bright. What we do is we take all these maps, we average them together, and we get our final data product, which is this map. This is just from 10 hours of data. This is comparatively a very small amount of data, but we're already getting it to observe 200 square degrees of sky. So for some comparison, the moon is about a degree in size. This is like 200 moons all in one image. So it's a very big area already. Right, so everything I've said so far about intensity mapping has maybe oversold it and made it sound far too good to be true. It's very easy. You just get a radio telescope, scan the sky, get all of your lovely data, do some analysis and win a Nobel Prize, hopefully. But it's, of course, never that simple. Because the way we do intensity mapping, we're just scanning the sky, recording all emission that our telescope receives. We're then going to be vulnerable to all other sources of emission, coming from the sky, coming from planes, coming from satellites, all these things. So we have all of these problems to deal with. So the stuff we're interested in, these are like full sky simulations in this demonstration. We're interested in the cosmological H1. That's, by the way, the neutral hydrogen is what I mean by that. So these are the 21 centimeter maps that we want. Everything else is contamination. So these, what we call here foregrounds, that's emission coming from within our own galaxy. So stuff like synchrotron radiation and free radiation. They're these very bright processes that will emit signals right in the frequencies that we observe at. Okay, so this is stuff put right into our data. And unfortunately, these can be about 1,000 to 10,000 times brighter than the cosmological hydrogen, the 21 centimeter emission that we want to see. And then we also have, as I briefly mentioned already, what we call RFI, radio frequency interference. This is one of the the arch nemesis of any radio astronomer. And this is something we're having to spend a lot of time trying to understand and contend with. Even the telescope itself will inject some contaminant into our observations. So we tried to supercool these instruments using cryogenics, but they're still just about hot enough to inject their own radio signature coming from the thermal effect of the electronics. So we have all of these challenges to overcome, and that's why we're doing this pilot survey, to demonstrate that we can, with Meerkat, overcome all of these challenges and do some cosmology with them, detect some cosmological structure within these maps. Yes?
Get that comes from having the multiple telescopes.
So the depth comes, we actually can, the observations we do simultaneously observe all frequencies, in other words, all wavelengths. So that makes us sensitive to lots of different amounts of redshift in 21 centimeter emission. Okay, so all we need to do, if we can clear all of these contaminants, the only thing we're going to be left with is cosmological hydrogen. Okay, so, and then we're going to have these maps at different frequencies, and they're going to correspond to different redshifted amounts of hydrogen. So this is how we get these three-dimensional maps, and that's how we get the depth. No more hands. So if we can successfully clean all this data, then maybe we'll be onto something. So this is a very complicated process, which I spent most of my PhD trying to understand. So please ask me questions about this if you have them, but I don't have time to go into exactly how we do it. But we do have processes which will clean these foregrounds. So what you're seeing here, these are like the raw observations of these this pilot survey, and underneath is the foreground cleaned equivalent. So what you'll notice, one thing to point out, is this color bar here is showing the temperature range. This is essentially like the intensity of the light that we're receiving. It's measured in temperature. And there's this example here, it's measured in kelvins, which for all intents and purposes, you can say is equivalent to degrees Celsius. But the thing to point out is this is in Kelvin. This one on the bottom here is in millikelvin. So this map's essentially dropped by about a factor of 1,000 in terms of its brightness. And what that means is we've removed a big chunk of this very bright foreground from the data. And hopefully what we've left behind with is the good stuff. The hydrogen traces the large-scale structure of the universe. Yes? Excellent point again. So these are essentially temperature fluctuations, I guess is how you'd say it. Yes, so that's a really good point. So for Kelvin, yes, exactly right. The absolute zero is zero. You can't have minus Kelvin. So yes, this is a temperature fluctuation map. Because that's exactly how we measure the hydrogen signal. Did I see another hand? I don't think so. It might have been the same question. Yes, yeah, no, good point. I should have pointed that out. So what we now want to test is within this foreground cleaned map, how do we know that we've just detected some cosmological signature? How do we know it's not just a load of satellites or noise or mobile phones going off? So the way we do this is we use this very powerful process in cosmology where we combine different telescopes. The reason this is very useful is, as I've shown in this demonstration, if we take radio observation, like the intensity map we just taken with Meerkat, and then we also take an optical observation, so this is a telescope using visible lights, like a galaxy survey. If they're both observing the same part of the sky, the same volume of sky, then the signals they both get coming from the cosmology, they're both tracing the underlying large-scale structure, their signals should be correlated, okay? Wherever there's structure in the sky, the radio telescope will see that, and the optical telescope will also see that. So you'll get some correlation from that signal. However, the contamination that both these telescopes have, because they're so different, you can see just how vastly different they are. Things like the radio frequency interference, the foregrounds that are in the radio maps, they won't be in the optical maps. So the contamination will be completely uncorrelated. So when you combine these observations together, in what we call a cross correlation, these contaminants will drop out, be uncorrelated, and we'll just be left with the signal. So this is what we use to test whether we're seeing some structure within our Meerkat intensity maps. What we did is this first pilot survey, we got it to, by design, overlap with this pre-existing galaxy survey in the optical wavelengths. So this is called the Wigglesy 11-hour survey. It's essentially just this conventional approach where you detect all these galaxies and they should trace the underlying dark matter field. And these galaxies have been gridded up here onto the same spatial coordinates as the intensity map. So this is just plotting the number density. So it's just all the galaxies counted up divided by the volume of the pixel. So what we're now trying to test is, does this final foreground cleaned intensity map that we get from Meerkat, does this correlate with this galaxy field? Because if it does, then we know we're detecting some structure within the intensity map, and we know that this technique is hopefully going to be then the future for cosmology for scaling up. Unfortunately, that's exactly what we saw. This is a plot from a couple of years ago now. This is the first pilot survey we did. What I'm showing here is what we call a power spectrum. But essentially, it's just measuring the amplitude of correlation at different scales between these two data sets. Okay, so on the x-axis, you essentially have the different scales. Confusingly, large scales are the small numbers here, and small scales are the bigger numbers. But if we had no cosmological structure within our intensity maps, this power spectrum here would be consistent with 0. So all these data points would just basically be fluctuating around 0. They'd be consistent with 0. That's clearly not what we see. You get this very strong indication of a positive correlation here. This is saying, this works out as well for people who know this sort of thing, there's about a 7.7 sigma detection of this cross correlation. So this is a very strong detection of this correlation. What this means is, yes, we are detecting some cosmological structure within these intensity maps. That's only a tiny amount of data as well. So yeah, this was the first detection of its kind, and this is what we're taking on now to try and scale up and do with hopefully future Meerkat observations and the final SKA as well. So I've just got this final slide to wrap up on, just to tell you, hopefully convince you that this is going to be the future of cosmology. So because we at first had to prove that this technique worked, which we've now just about done, what we're now getting is lots more observational hours. We're being awarded much more observation time. So from that pilot survey observations that I just showed, just to remind you, that was 10 hours of data. Last year, we took 270 hours of data. This year, we're doing 500. That's started this weekend. And the next calendar year, we're doing another 500. So the amount of observations we're now getting is just blown up. And we're also doing it with a different receiver. So we're getting a much bigger frequency range. What that means is we get much deeper maps in terms of redshift. So we can do much bigger skies because we have much more observation time, much deeper in terms of how much redshift we can cover. So the volumes are just going to be, I think the workout is about a factor of 400 bigger than what we've observed so far. So it's really exciting times ahead. We're going to hopefully try to really push demonstrate what this technique can do for the future of cosmology. So I'll wrap up with some just concluding remarks now. So yeah, hopefully I've introduced some of you to why cosmology is hard and why we're so far doing quite a bad job in trying to understand it. We sort of have a model for the universe that works, but for 95% of the universe, we don't have a physical description for what its components are. So this is a big problem that we're trying to make progress with. In order to make progress with it, we need new observational techniques. And this radio intensity mapping technique is one that a lot of people are excited about. And in just the last few years, we've been able to show that it can work with real data. We've been able to show this thanks to this pilot survey that we've done with Meerkat and this cross-correlation detection. So now what the future holds is we're going to go and try and do with all this new observational hours, this huge survey shown in red. This is a map of the full sky that I'm showing here. This is about a quarter of the full sky that we're going to be able to map with all of these observational hours. And this will be done in the pre-SKA era. Then SKA will come along in the next 2 or 3 years and take over. And we'll be able to go to even bigger skies as well. So that's everything I wanted to say. So thank you so much for listening. And if there's any more questions, I'm happy to take them. Thank you.
Awesome.
You're about radio. What are the worst sources that you have stories? You have crowd things that will go out with experience.
So yes, so I did have a couple of slides on it, I think, which maybe I can just bring up now.
That might.
So this is very unprofessional, but just to see if I have some good slides on it. So one of the worst A lot of people think that satellites are the worst for us. In general, for radio astronomy, they probably are. Satellites are sort of like this plot here shows, they're everywhere. And so in general, satellites are one of the worst things. They're very bright signals. Most of them, we don't know where they are as well. Some of them we know when they are tracking over our observation, so we can avoid them. Most of them we don't know. Fortunately for us, most of the satellites, things like Starlink, Elon Musk's thing, that doesn't emit in the same frequency range as us. So that's not too bad. One of the biggest problems for us comes from planes. So planes, as this plot here shows, are absolutely covered in these what we call distance measuring equipment, stuff to measure all the things you need to measure on a plane. And they all seem to emit within the frequency ranges we see. So this is a real problem for us. And this was best demonstrated in lockdown when all the planes were grounded. So this plot here is showing pre-lockdown, all these bright points here where we have to flag basically all our data. Where it's one, we've had to flag everything. And after, well, in lockdown, all the planes are grounded. We had this absolute golden age for radio astronomy where we could observe all these things. So this is a real problem. And the other one is mobile phone towers. They're probably the two biggest ones, planes and mobile phone towers. Even though we put these telescopes and meerkats in one of the most radio quiet regions in the world, it's so sensitive that it will still pick up a radio phone tower about 50 kilometers away. So yeah, these are the two biggest sources for us. So, well, so the planes aren't static. The planes
will mobile phone towers would be a lot easier to move.
Potentially. So the problem, maybe I even have a slide on this as well. So yeah, this is good to explain. So yes, I see your point. So the radio phone towers are static. The problem is though, we're kind of observing in a different point of the sky all the time, even though we want a fixed cosmological volume. Where that is on the sky kind of moves all the time, depending on what time of night you're observing. So what that means is the exact tower changes position all the time. And it's very hard to exactly calculate this. And it also injects this kind of weird structure you see. These stripes here, we happen to do an observation where the tower, for some reason, the nearest mobile phone tower to us, was turned off. We don't know why, probably for maintenance. And it's suddenly turned on. And you see these stripes that it's injecting into the maps. And I'll just quickly show this animation to show because it's quite useful to understand it. What we're doing when we scan the sky, our telescope's going back and forth like this at a constant elevation. And as it's doing that, you'll notice the background sky is drifting across the telescope. Okay, this is obviously sped up. And what that does, it draws these lines on the sky to get our observations. But what this is doing in terms of the mobile phone tower, the mobile phone tower is coming in and out of these peaks and troughs of our what we call the point spread function of our telescope. So we're getting these bright stripes injected into the map every time it hits these peaks. And we call this zebra RFI, one of the sort of first collaborations to encounter this thing because of the way we use the instrument. So yes, I see your point. It's static, but it's unpredictable in that it's different every night. It's different with every observation. So it's still very challenging to remove. At the minute, we just have to delete it. But we're trying to do better than that and come up with some clever way to actually remove it instead of just delete everything. Yeah.
What your general opinion of dark matter is, and any reference to MOND you might have with that.
Yeah, so maybe just to quickly explain to the audience. So MOND stands for Modified Newtonian Dynamics. What it is, it's one of the early shouts of how we can, rather than have some missing mass to explain this dark matter problem, we instead change the laws of gravity. We say that gravity is wrong. The Einstein's theory of general relativity or whatever needs some modification. And MOND is one of the most famous theories for doing this. So it has, on that footing, it seems very sensible. It's a good place to start. The problem with most modified gravity theories, including MOND, comes to this point that I touched upon. When you try to build these universes in computers, it's so hard to do with a theory like MOND and not having any dark matter in. Universes that literally don't look the same as what we observe. The structure, the exact statistical distribution of the matter doesn't look the same as what we observe. So that kind of gives us some evidence that it's probably not as favourable as a theory, instead of just having some missing mass. So,
just an extension to
yes.
that question. What's your view on the variability of H0?
So yeah, again, just a quick 30-second background. H0 is known as the Hubble constant. the reason it's very interesting, what it measures is essentially the expansion rate of the universe. I said that the universe is expanding. You can measure how fast that is expanding. That number on its own is not particularly interesting. What is interesting is that if we measure it using different techniques, some by measuring very local stars within the universe, some doing cosmological methods like I do, you get a disagreement on that answer. You get quite a big disagreement as well. It's about a 5 sigma, very big significant difference between these measurements. So clearly something is either wrong in those observations of the local universe that we're doing, or we're missing something in our cosmological model. So yeah, my opinion previously was that there must be some kind of systematics coming from the local universe observations from the supernovas. That was my favorite theory, but recently we had this, I kind of touched upon this result from DESI, which actually was suggesting dark energy might be evolving, changing through time. That could be a solution to this problem. If you have dark energy changing, it should actually correct for this cosmological constant that you measure, sorry, the H0 that you measure coming from the cosmological approaches. So I think that could be a resolution to this tension that you're talking about. Yes.
So you have Java Bank as a plane, you have Australia, Africa, massive great deserts. So I don't know, Java Bear is like Mama Bear or something, but there's much more interference. You've got an airport around the corner. You're surrounded by the urban.
Exactly. Yeah. No. So
I guess it was built when it was built, but it seems weird to have the three. So what's Jodrell Bank's? I'm going to say aim, but I mean I don't mean that. But
yeah. So I do get your point. So for the purposes of the SKA, we're not actually using the telescopes at Jodrell Bank. We are just using it as a headquarters, really, global headquarters, and we will just be using the telescopes in South Africa and in Australia. But saying that, the telescopes at Jodrell Bank are still doing world-class science, but they have to do a certain amount of science that doesn't require the sensitivity that I need to do the very, very distance, because I'm detecting something very, very faint. And if I go and do that in Manchester or just outside of Manchester, I'm just going to get swamped by, like you say, all the airport noise, all the surrounding populations. Everyone who goes there's probably got a phone on. So yeah, that's why we won't be able to do this kind of observation.
it's obviously still very useful.
Very useful, yeah, it still does. Yeah, many of my colleagues at Manchester University are using telescopes, which are literally based at Jodrell Bank. So it's still doing world-class science. So it's very useful to use.
Anybody else got any questions? No?
Yeah, so if I've understood you right, although you talk about detecting dark matter and dark energy, mapping it, we haven't actually detected any. What we're doing is we're mapping the places where we infer it ought to be. We haven't actually got any evidence there's any dark energy there yet.
Yes. I think yes, that is a fair point. So we make it's an assumption, but we have validated the assumption, which I'll briefly explain. So we assume that everything we're looking at, so the hydrogen or the galaxies, they trace dark matter. We do have one way of pretty much directly detecting dark matter, and it's known as gravitational lensing. Okay, so the way we do this is anything with a large amount of mass, like a big clump of dark matter, that's going to bend the space-time. That's how general relativity works. And because you're bending space-time slightly, that means the light's going to curve around these big clumps of dark matter. And that's going to lens everything behind it. So what we can do these lensing surveys that will pretty much map the dark matter where it is, kind of indirectly, but also directly, because it's the thing that's doing most of this bending is the presence of this dark matter.
Does a black hole count as dark matter?
No. So yeah, a black hole is for a cosmologist is almost insignificant because they're just so small. Even though they do have quite a lot of mass, they're always within big galaxies, and even the galaxies themselves are point-like. So yeah, so a black hole wouldn't. I mean, it will have some dark matter in it. It will just have all mass that's collapsed within it, but no, it wouldn't necessarily be a dark matter source.
Because if you were detecting dark matter, you couldn't map it against the optical things, because the optical thing you see dark matter, so you could detect it.
Yes, I think I followed, but yes, I think I agree. Yeah.
Anybody else got any more questions? No? Well, thank you very much again, Steve.
Yeah, pleasure. Cool, thank you very much.